In this video, I will present a simple derivation of the Lagrangian dynamical equation. In Chapter 7, we're introduced to the Lagrangian, which we find is the difference between the kinetic and potential energies. And for a mechanical system, if you define the Lagrangian, if you can define the Lagrangian, in terms of a generalized velocity and position coordinates, you find that the Euler-Lagrange equation applies so that the time derivative, total time derivative of the partial q dot derivative of the Lagrangian minus the partial derivative with respect to the qi derivative, that those two things together is 0. And as we discussed in class, this works out to be equivalent to Newton's F equals ma. But I didn't actually describe how you got to that, and the book doesn't do a real thorough job of explaining where this comes from, except to refer to Hamilton's principle. And so here I'll present a simple derivation of this dynamical equation and show how it is totally equivalent to F equals ma. And so we begin by imagining a massive particle confined to some surface. So here's our surface, here's our massive particle. Now it helps to maybe think of this particle as being a car on a roller coaster, and the particle is trapped on the surface of the roller coaster track. So we imagine that the particle is confined to the roller coaster track. Now the position of this particle in principle can be given using Cartesian coordinates x, y, and z. And so then the position of the particle will be just a position vector x, y, and z. And so in principle, we could model the dynamics of this roller coaster car using Newton's laws, F equals ma, and we can work out the dynamics in these three coordinates. But the dynamics will be quite complicated because the particle is confined to this roller coaster track, and the roller coaster track can have a pretty complicated shape. In that case, the dynamics in the x, y, and z coordinate system will be pretty complicated. In addition to potentially, in addition to the gravity, which is going to pull down on our rail car, we're going to have forces of confinement in the rail car. So basically, the track will confine the roller coaster car to the track, and that represents a force of confinement or a force of constraint, which forces the particle to remain on the surface. And it could be a roller coaster track, or any kind of surface. So those forces of constraint are really important. It can be quite complicated, and if we were going to do the whole problem in x, y, and z, we'd have to include those forces of constraint the whole way through. That would make solving the F equals ma equation pretty complicated. But we can employ an idea called virtual work to eliminate the forces of constraint and only think about the dynamics of the system along the coordinates where motion is possible. So in this case, we'll use coordinates that actually follow along the track and ignore any motion perpendicular to the track, which doesn't happen anyway, but which we would have to include. We would have to consider accelerations in those perpendicular directions if we were going to apply Newton's law in the standard Cartesian coordinate system. So again, think about our massive particle confined to a surface. That massive particle is subject to two different kinds of forces. The net force on the particle will be a combination of applied forces, which we'll call capital F. These are forces like gravity, they might be even friction, but we're going to consider conservative forces here. So just the applied forces, so things like gravity, maybe a magnetic field, anything like that. And then there'll be something called the forces of constraint, which we'll call little f. This will be the forces of constraint. And as I just described, if for example, our massive particle were a roller coaster car, the forces of constraint are the force between the track and the wheels, which keeps the roller coaster car stuck to the surface of the roller coaster. Now, we imagine that as our massive particle is moving along the surface, we imagine that we can move it along the surface a teeny tiny amount, just a teeny tiny amount. We're going to move it virtually. So in other words, we're going to keep time fixed, and we're going to imagine that the particle moves a teeny tiny amount in the surface in a direction delta r. So delta r is a little bitty vector that points along a direction that the particle is allowed to move. So for example, again coming back to our roller coaster car, delta r cannot point perpendicular to the roller coaster track because the massive particle is not allowed to move perpendicular to that. So delta r is allowed to point in any direction it likes as long as it's consistent with the constraints, as long as it does not point in a direction that the particle cannot move. Okay? And so then we imagine the virtual work done by our two forces in moving the particle along delta r. So that virtual work is going to be the sum of the two forces dotted into the virtual displacement vector delta r. So we're taking these two forces, the applied forces, say gravity, anything else like that, and the forces of constraint, and moving the particle virtually in the surface somewhere, and asking how much work is done in that case. So most of the time, a lot of the time, these forces of constraint, they can't do any virtual work. So again, coming back to our roller coaster car, the forces of constraint point perpendicular to the surface, right? They pull down on the car, for instance, to keep it trapped in the track. And so these forces of constraint can't do any virtual work. In other words, little f dotted into delta r, that has to be 0. At least we're going to consider forces of constraint for which that holds. So the only force of constraint that can do any work is the applied force. And now taking a little bit of a detour, recall Newton's second law that the force on a particle is equal to the time derivative of its momentum vector. The time derivative of the momentum vector is mr double dot in the case that we're going to consider here. And so the virtual work done by our applied forces is going to be equal to the dot product between delta r and p vector dot. And we can rewrite this equation, bringing p vector dot into the same side as the applied forces, dotting them both into the virtual displacement, and then that, by definition, has to be equal to 0. This equation here is referred to as D'Alembert's principle. The idea basically is that any time derivative of the momentum vector has to be compensated by a force. This is something you're very familiar with. We're just writing it in a slightly different way. And then we're taking this funny dot product with a virtual displacement. As it turns out, this virtual displacement lets us do a lot here. Already you can see by considering virtual displacements and virtual works, we've gotten rid of the forces of constraint in the problem. And so by considering virtual work, we actually remove the forces of constraint which don't do any virtual work anyway. They're important for the dynamics of the problem, but they're actually not all that interesting. And so by writing out the virtual work in a system, we've eliminated those forces of constraint, and as we'll see, that actually simplifies the problem. So now let's go to work on this expression in here, and we'll show how we can convert this expression using our generalized coordinates, and then work our way toward the Lagrangian. And let's just clarify one point that we're going to need in order to proceed. Recall that we have a position vector r, and we're thinking about r as being defined in the Cartesian coordinate system, so x, y, and z. Well, we don't have to use a Cartesian coordinate system. We can use really any coordinate system we like. And if we're specifying the position and velocity of a single particle, we can use any three coordinates that we like to specify the position and velocity. As long as we use three coordinates to specify the position and velocity, the position of that single particle. So for instance, one kind of generalized coordinate system that you're used to, we can imagine converting from our Cartesian coordinate system into, say, polar coordinates, r, theta, and phi. And so in this case, r, theta, and phi would be our generalized coordinate system. And so we imagine that our position vector is a function of our generalized coordinates. In the case of a single particle, it'll be a function of three generalized coordinates, but we could have much more complicated systems where we had an arbitrary number of generalized coordinates. Of course, our velocity vector is just the time derivative of the position vector, and now we can write, using our generalized coordinates, we can write the time derivative of the position vector. And if you recall your chain rule, a time derivative of a function, which is itself a function of other variables, is going to be the derivative of that function with respect to each of the generalized coordinates, qi, times qi dot, so that's the time derivative of qi, plus any explicit dependence that the position vector has on time itself. So let's take an example. Let's imagine that we're just working in 2 dimensions, and we're going to convert from x and y into the polar coordinates r and theta, and let's work out what the velocity vector looks like using these generalized coordinates r and theta. Okay, so our position vector written in Cartesian coordinates is x and y, and then the x and y coordinates we can write as r cosine theta and r sine theta. We just argued that the time derivative, the velocity vector, is going to be this expression here, so the qi derivative of the position vector r times qi. Okay, and so let's work this out for each individual coordinate. So for instance, we want to take the derivative with respect to the r coordinate, and so that's going to give us cosine theta, sine theta. Then we need the second derivative here, the derivative with respect to theta. That's going to give us minus r sine theta plus r cosine theta. And now our vector dot is going to be cosine theta sine theta, right? So that this right here is this, and we're going to multiply all of that by r dot. Now keep in mind, this is the radial displacement, the time derivative of that radial displacement, so the distance from the origin, plus minus r sine theta plus r cos theta, both times theta dot. So again, this term here is that derivative with respect to theta, and then we've got times theta dot. And so putting it all together, the velocity vector in the r and theta coordinate system can be written in this way. And so again, that's just highlighting how you actually apply the relationship between the velocity vector and the generalized coordinates. Okay, so coming back to D'Alembert's principle right there, we also need to think about how will we write the virtual displacement vector in terms of the generalized coordinates too. So as before, very similar, a little change in the displacement as written in R is going to be equivalent to, maybe you can guess this, the derivative of the position vector with respect to each individual generalized coordinate times the virtual displacement along each individual coordinate. And keep in mind, we'll come back to this point, keep in mind this virtual displacement is arbitrary. You can be displacing the particle in any direction you like, consistent with the forces of constraint, consistent with the constraints on the system. So you can go up, down, left, sideways, whatever you want to do. Delta R is totally arbitrary. And as it turns out, well, and therefore, these displacements, delta Qi, are arbitrary. You can displace along R or theta or phi, whatever you like. Each of these displacements along the generalized coordinates are arbitrary and independent. So you can displace along the different coordinates different amounts. And that's going to be a key feature later. These displacements in the generalized coordinates and of the Cartesian coordinates are arbitrary and independent, as long as they are consistent with the constraints in the system. Okay. So now, what we're going to do is work out what this time derivative of the momentum vector is in terms of these generalized coordinates. And that's going to give us actually That's going to get us most of the way to the Lagrangian dynamical equation. So let's look at that next. Okay, so that term having to do with the momentum time derivative dotted into the virtual displacement. We just worked out what a lot of these things are. This is going to be equal to mr double dot dotted into delta r vector. Delta r vector we just worked out is, in terms of the generalized coordinates, excuse me, let me take a step back. Employing our relationship, our definition for the displacements in terms of the generalized coordinates, we're going to rewrite this expression here as mr double dot dotted into the qi derivatives of the position vector delta qi. Hopefully you recall this relationship that the velocity vector, r vector dot, can be written in this way in terms of the generalized coordinates. We see here that the velocity vector has this explicit dependence on the qi dots, right? So there's this dependence right here. And so what that means is that the partial derivative of the velocity vector with respect to qi dots, well, that's just this term right here. In other words, the partial derivative of the velocity vector with respect to qi dot is the same as the partial derivative of the position vector with respect to qi. And we're going to take this relationship and replace this guy in here with this guy. Okay, so again, we've got this term from Dalibard's principle. We've worked out that it's equivalent to this over here. And now we're going to take another little detour and think about what the time derivative is of this expression, mr dot. That's the velocity vector you can see right there. Sorry, not the velocity, excuse me, the momentum vector. All of that dotted into this expression right here, okay, which is almost what we have up here, but not quite. We've got one dot here, okay? So the time derivative of this whole expression is going to end up being mr double dot dotted into, oops, this partial here, plus mr dot dotted into the qi partial derivative of r vector dot. So basically, this time derivative is independent of this partial derivative here, and so we can take the time derivative inside the partial, and we end up getting this expression here. So what this shows us is that this, which is equivalent to that, can be written as the time derivative of all of this business minus this. So in other words, we have this now. That term is going to be equal to a sum, and we'll put all the things that need to be summed in the square brackets here, of the time derivative of this expression minus that expression. And this is starting to look kind of suspiciously like the Euler-Lagrange equation. We've got a time derivative here. We're going to turn this guy into a qi dot derivative. We'll see that in a second. Okay, so again, exact same expression we just had. P vector dot dotted into the virtual displacement is equal to this big sum here. Now recall that we've already argued that the qi dot dot partial derivative of the velocity vector is equal to the qi partial of the position vector. So we can make this replacement in here. We see that we have r dot here and r dot here, so that's actually just v. And so this whole expression is going to turn into this expression here. And now we should start to get really suspicious that we're creeping up on our Euler-Lagrange equation. We've got here a time derivative of a partial with respect to qi dot. Here's a qi dot derivative of a velocity. This mv vector dotted into a v vector, that starts to look a lot like a kinetic energy. And indeed, you can show that this expression here easily turns into this expression here. So now basically we take our qi dot derivative on the outside. What's left here is 1/2 mv squared. This expression over here turns into this expression, qi partial derivative of 1/2 mv squared. So you can see here we have the kinetic energy with kinetic energy. Let's go back to our D'Alembert principle now. Okay, so here we are back at D'Alembert's principle. We've shown that this first term can be rewritten in this way. So here's the time derivative of the potential energy, and we've got to multiply this by the virtual displacements along the generalized coordinates. Then we do a little sum here. And then we've got to subtract from that the virtual work done by any of the forces, any of the applied forces. Now recall our expression for the virtual displacement in terms of the generalized coordinates means that this expression can be written. This expression over here can be written as this here, and so we can basically take all of this inside of this. And there we go. Okay, we're almost there. We're almost to our Lagrangian dynamical equation. The next thing we need to do is to show that this expression here can be rewritten in terms of a potential. And so at this point we're going to assume that our forces, our applied forces, are conservative and that they depend only, and therefore they only depend upon the positions. They're path independent and they depend only on the position. There's no velocity dependence, there's no time dependence, and that will allow us, as you've seen in previous chapters, to write the force in terms of a potential. Okay, and so just to remind you, force, if it's conservative, can be derived from a potential. And so here's the gradient, and now we're thinking of the gradient as being in Cartesian coordinates of a potential. Recall that we're interested in the virtual work done by that force, and so that's going to be equal to the gradient of the potential dotted into this little transformation derivative here times the virtual displacement in the generalized coordinates. This expression here, you might expect, is actually equal to the qi partial of the potential energy. Okay, so this is actually equivalent to that. And so now let's take this. Now remember that we've assumed a conservative force. Therefore, the qi dot partial derivatives of the potential energy are 0. Okay, that's going to be really important when we take this term back into our D'Alembert principle. Okay, so again, coming to our back to our D'Alembert's principle, we found that we can rewrite our force, our virtual work of our force, in this way. And now we see Lagrange's equation pop right out. We can see here that we can combine these two derivatives here. That'll give us minus the qi partial of t minus v, and there's our Lagrangian right there. We can also take q and put it into the qi dot derivative here, because remember, v, the potential energy, has no dependence on qi dot, and so the qi dot derivative of v is just 0. And so this whole thing works out to be a sum over I time derivative of the partial of t minus v with respect to the qi dot with the time derivative up front plus, minus qi dot, the qi derivative of, again, t minus v. Okay, and so we know that D'Alembert's principle tells us this is all equal to 0. So here's our Lagrangian right here. Now, recall that this whole thing is a sum, so we're summing over all the generalized coordinates qi. And so, strictly speaking, D'Alembert's principle says that this sum is equal to 0. But remember, I said earlier that these virtual displacements are independent and arbitrary, meaning the displacement along one coordinate is totally independent of the displacement on the other coordinate. And so the only way that can be true and have this sum work out to be 0 every time is if everything inside the square brackets is itself 0. And so that means that everything inside the square brackets is 0. In other words, this minus this has to be 0. This is our Lagrangian. This is the Euler-Lagrange equation. And so that's how, for some very simplifying assumptions, you can work out the Euler-Lagrange equation using the principle of virtual work, which allows you to ignore those forces of constraint. So remember, that's a really key assumption right at the beginning, is that we're thinking about this in terms of virtual displacements confined to the surface in which the particle moves. That allows us to ignore those forces of constraint and work out the dynamics of the system without having to even think about those forces of constraint, which again, don't do much to dynamics anyway.